Okay, I'm gonna share my solution to, well, it's not my own solution, but I mean, one of the solutions, which is gonna be also quite interesting to showcase. Is this one for unique paths? So it's a classical problem, medium difficulty, and then these are the companies that have asked it. So Amazon 6 times, Facebook 6, Microsoft 4 in the last like 6 months, and 6 months to a year. Well, we have Google also, like as I said a lot of times, Apple, Adobe. Okay, so this is the problem statement. There is a robot on an n by n matrix. The robot is initially located at the top left corner. The robot tries to move to the bottom right corner, right? This is the target. The robot can only move either down or right at any point in time. Down, down or right. Given two integers, m and n, which are of course the dimensions of the matrix, return the number of possible unique paths that the robot can take to reach the target. Okay, so again, this is like another like combinatorial problem, counting problem, as we saw as well with generate parentheses. So I'm gonna also link that because it's kind of similar as well in a sense. The strategy is quite similar. So I'm gonna also link to that problem when I upload this video to the YouTube channel. Okay, so let's see some examples here. So this is gonna be quite complicated to like actually walk through, but for example, can I where is it drawing? Yeah, here. So for example, can I move this? Can I move this? At least. By the way, that is my wife that just passed by. And actually, to tell an interesting story, the other day she showed me her high school grades, and then I noticed she had like a course in informatics that, and then she had like a B plus or a B in programming. It said she was making like scripts or computer little small programs in VB script. That's like a very old language, VB script. It was, I think it's like a Microsoft one. And I was very surprised because she never told me anything about it. And of course, she said she doesn't remember anything, but I highly doubt it. I think she's hiding a secret from me. But anyway, let's start to back to the problem. Okay, so for example, this one can have one path here, right, to the finish line. I can also have this path, right? And then it can also, for example, go like this. It can also go like this. It could also like come down, right, down, and right. So the total combinations of all these paths would be 28, right, if we count them. And then, for example, with a much smaller grid, the total combinations will be 3. And it's kind of like the one we are going to visualize. Clear all my drawings. Okay. So then I'm gonna come here. I'm gonna clear this Jamboard. And I'm gonna copy these things here. So we can even just do it. Yeah, okay. It's 3 by 2, fine. 3 by 2. And then let's say this is our starting position, right? And then this is our target. And then we can see that we have one way. Then we have 2 ways to get to the target. And then we also have 3 ways, which is this one, right, down, and right. So we have a total of 3 paths, 3 possible paths. So one way to like think about this problem is we can think about it like in grid states or matrix states, right? So it's also like a good idea to visualize these types of problems somehow, like that involve recursion. in the following way. So we know like we can move there's two types of movements we can do, right? So two types of moves, which is down and right, right? And this is similar, for example, again, with the parentheses problem, like the generate parentheses problem, like we could create one closing parentheses or one opening parentheses, right? And here, instead of parentheses, like we can move. We have two options, move down or right, at any given moment in time, right? While we're iterating, where we're trying to find counting these paths. So if I go here, I'm gonna copy this here. So if I go here, just thinking how I can, yeah. So we have here, I'm gonna just store, oh, I don't even need to be so fancy actually. So let's say our first grid will be 3 by 3. Although it's not the one we have here. But okay, let's just start 3 by 2, right? So we have three columns by 2 rows. And then after that, these things. Then after that, we have 2 possibilities, right? Move down or right. So let's just put here like down and right. But what does that actually mean? Let's go back here. What does that actually mean? So if we come here, right? So this is our initial state of the board, right? It's here. And I'm gonna just erase these guys here because we already like visualize these paths. So we can, right? These are like our initial state. Let's just put it here in blue, like all of this. But when we move, for example, like let's move in the next step, like let's move right. Let's say this is like the other state, like prime, right? Our second thing. But then here, like we can consider that if we move here, then we have like a reduced grid, or let's say a reduced search space, right? We will only be considering this section of the board, right? Not this to the left. And once we move here, of course, like instead of having 3 paths, we would have only 2 paths, right? Here and here, okay? And then, for example, let's say that we decided to move down now, right? In the next iteration. So we have this state here. It's like prime, right? And what do we have now? Like it's reduced. Now we only have this, right? So we're kind of like cutting our solution space by some fraction each time, right? So now we're here in state prime. Well, obviously we only have one possible path, right? One possible path. So once we have this, we have one row and 2 columns, right? So that will be 1. But then let's say now our other state is gonna now move right. Right, so now we're gonna have this one, triple prime, the last one. So the last one is basically we're at the same, like our grid, our matrix wouldn't really be a matrix anymore. It will be like a singularity. So we are at the same position as our target, right? So then this will basically could be considered as like what would this be like? Yeah, we can call it like 0, something, right? 0, something. And in that case, of course, there's no possible paths. So then basically this will be 0, right? So just because of that, so there's like some base case, right? Like if we or if position equals target position, 0 paths, right? And now I'm gonna draw the same in the other side, like what we did here. So I'm gonna copy this here, perhaps here. So for example, here, like, okay, we decided to move right. So what does that mean? That we have here 3 columns. So if we decided to move right, we will have this, a grid of 2, 2, 2, right? So basically 2 rows and 2 columns. Well, let me just maybe do this better. So we have 3 columns, 2 rows. So 2 columns, 2 rows, right? So if I come here, so we moved right? Here, what I'm doing. Now we have this grid, 2 rows and 2 columns, right? Two, yeah, whatever, 2 columns, 2 rows, and right. So basically what we're doing here is that we are subtracting, right? We're subtracting 1. It's basically the same as doing this. Like we come here and we're basically subtracting 1 column. So instead of 3 columns, we have 2 columns. And then if we want to move down instead, we want to subtract row, right? So then these 3 columns will remain the same, but it will be one row, right? 3 columns and 1 row. Okay. So, and then we can do the same branching. For example, here and then here, right? So we come, okay, let's also draw this one here. And then for here, like if we go right, when we reduce still the search space, 1, so 2, oops, sorry about that, row stays the same. So 1 column and 2 rows. And then here, it will be 2 columns and 1 row. Okay, 2 columns and 1 row. And then here we will have, of course, 0 rows. No, sorry. This is rows. So we move up. Sorry, this is right. It's kind of confusing here because this is actually should be called right. Right. Right, and then down. So let me just go 3. So right column. So yeah, here, down here, cool. And then here we have down. There's gonna be, yeah, 1 row. Cool. So yeah, and then this one is here. So there's gonna be 0. Oh, this is gonna be 1 here. 1 row. There's gonna be 1. Sorry, this is gonna be 1 row, and then this is gonna be right. So it's gonna be 1 to the right. So this is still gonna be 1 row. This is gonna be 0 columns now. So we reach the singularity. And then here we will have column, right? So we're still gonna be 3 columns, and 0 rows. 3 columns and 0 rows. So here we reach like some singularity, right? Some base case. But basically this grid will be 0 paths to the target. And also this one. So then let's keep shifting down. So this one, we still need to like flesh this out here. And then here, for example, we're gonna move down. So we're gonna remain here, and then we're gonna have 2 0 rows. And then here we're gonna have 1 column, 1 row. And then here we are going to also move to the right. So we're gonna have 0 columns and 2 rows. And here we are gonna move down. So we're gonna have 1 column and 1 row, right? So then we know that this grid, for example, this grid here will return 1 possible path, as we saw in the diagram. This will return 0 paths. This will also return 1 path. This will return 0 paths. And for example, this one will also return 0 paths. This will return 0 paths. I think. Wait a minute, 2, 3, 0. Wait a minute. Oops, I made a mistake because this is actually going to be two columns, actually. Oops. 2 columns, actually, sorry. 2 columns. And then this one is going to be, yeah, this is going to be 0. But then this one, 2, 1, it's actually, yeah, we're actually, you see, repeating this branch as well. So that we're going to go to that later on. Anyway, so we have this and we have this, and we can actually repeat this thing here. Copy these guys. Okay, sorry about that. So then this will of course return 1, this will return 0. Okay, so now we are at the leaves, right? We reach this base case. Okay, so let's continue, right? So now this basically are our leaves. So these are, as I said, our base cases. So once like we reach this, we know that these two here, so this one should add up to 1, right? Because 1 plus 0 will be 1, and then here will be the same. This will add up to 1. This will add up to 1, or sorry, here. So 0, 0 plus 1, and this as well. 0 plus 1. This will add up to 1. Okay, cool. So then this one will add up to 2, right? And then it's because 1 plus 1 equals 2. And then here, this will be 1, right? So in this grid of 3 columns and 1 row, there's only also one possible solution, right? One possible path. And then here is 2 possible paths, as we saw here, right? 2 by 2, 2 possible paths. And then the other one, this one here, 3 columns, 1 row is basically this part here. So three columns, 1 row. There's only 1 possible path. Well, actually, it will be more this one, right? So where our target is here. Only one possible path here. And then after that, so 2 plus 1 is 3, right? 1 plus 2. So this is like the logic of this, right? So then as we are seeing, I mean, this could be kind of problematic. Like this would be basically the brute force approach. But we see, for example, that we're repeating a lot of things, like, right, this branch here, or all this subtree is repeated, right? And all this subtree here is repeated as well. And in a sense, like 1 column, right? Like 2 columns and 1 row is the same result as one column and two rows, right? Because they both return one. So in a sense, this is also another repeated subtree. And then we're gonna see how we can optimize this. But this is basically the visualization of this recursive tree, which is a binary tree recursive basically function, right? So now let's implement this solution. Okay, so this is the visualization. And one important thing to note is that we're seeing that we have overlapping sub problems, right? That are basically solved multiple times. And this is like a very small input. Imagine if this was like, 10 by 10, for example, like we will have a huge tree and we'll have so many repeating computations, right? Because they're like overlapping sub problems. Okay, so let's do this here. So basically, let's define our base cases. So let's first do like a function, and we're gonna say like let's call it like path solver, and then we are going to have also this as input, and we can just call m and n, and then we're gonna return the result. Oh yeah, okay. How do you do this in TypeScript? Should I be, I guess, this number? Okay. Oh shit. Okay, yeah, I can use the same logic here. So this is actually number. Okay. And it's oops, confusing here with Python. Okay, yeah. It's return something for now. Okay, so we have our base cases, right? So we have if m or if m or n equals 0, we know we will return 0. There's no path, right? So no paths to return as we are at grid space is a singularity. Okay, and the other condition we have is this one. So if m if either one of them is 1, right? There's only one path. So if m equals 1, we will return we will return 1. And okay, so these are our base cases. And then we will do the branching. So we will call this thing, and we will say, so we will say here, for example, we will move down. So that what that means is that we will say m minus 1 plus n. And then we are also going to have, and we can call this, for example, here. And then we're gonna leave this here, and then we're gonna decrease the columns, right? So we're gonna have n minus 1. So n is the column, m is the row, which is essentially what we're doing here, right? Subtracting. And then we are going to return this. Move down. Oh my God, I'm still doing Python comments. Move down. And move right. So then this is the part we're doing like the addition, right? The result 1 + 1, for example, like etc. So then this will basically start returning our results when we hit all the base conditions. And then this is gonna start like returning all the way to the top of the tree. Okay, so let's submit this. So okay. So for some reason, the output is 0. Interesting. Oh, shit, sorry. Ha, I see it here. M equals 0, and then this was, it has to be 1. Okay. Yeah, screwed up in these ones. Okay, yeah, so 28, 28. And then we have these ones here, right? 3, 7, da, da, da. So let's see okay, so for example, I'm gonna try like, let me just remove 3, 7, 3, 2. Let me just remove these. So let me try like something huge, for example, like 50 and then 50, right? To show you guys, it's gonna basically time out. And so have the value from okay. It's because this will generate the test cases are generated so that the answer will be less than or equal to. Okay, yeah, that will exceed this number here. So let's do something smaller. 10, 10, 10, and see if it times out. Okay, yeah, it didn't. So let's try again. Maybe 12, 12, perhaps. Okay, let's go bigger. 15, 15. Okay, still it's going. Come on. What's the combination here? Maybe the easiest thing is just to submit this thing. Let's submit it. Should time out. Yeah, there it is. Time limit exceeded. Okay, this was the correct combination, 51 and 9. Okay, fine. Okay, so that's the thing. And so the one, like, basically a way to optimize these problems is just to like create like a cache, right? So dynamic programming is basically that in a sense. So optimize, so dynamic programming, and then that basically is cache computation, right? Of course, the difficult thing about doing this is that it's very hard to visualize these types of problems, like what problems are overlapping. Like we see, these are overlapping, but it's very difficult to kind of do that intuitively. Here, it's done because it was drawn and visualized, but the complexity of like trying to see how dynamic programming can be applied to a problem, it just takes a lot of practice basically, and doing a lot of these types of problems and being able to recognize like the patterns. But overall, I mean, I'm not sure if like all of these types of like puzzles that involve like combinatorial or counting problems, like you can solve them like this recursively, like with the brute force approach like this. But I'm not sure if all of them have like, well, I'm sure maybe like if this solution exceeds the time limit, then maybe that's like a hint to say, oh, you need to use dynamic programming somehow to like cache the overlapping like computation, so you don't have like redundancy. So maybe that could be a hint. But just by seeing like a new problem and seeing, oh, that perhaps can be solved with dynamic programming, I think that just takes much more practice as well. Okay, so it's quite simple here. So we need to have like we can use like a hash map. And how would you do that in TypeScript? Well, I think should be like that. We can call it like hash map equals new map. Yeah, and then I think we can also just be rigorous and say type map. Okay, generic thing. So, okay, yeah, cool. Reminds me of C# days. So it's gonna be. How can we, what would be a good way to do the key? In this scenario. We know that the value will be a number. And the key, I mean, the key should be these coordinates here. So, right, the grid thing, right? M and N. What can be like? Maybe just like an object. Let's, would this be it? Object? Perhaps. Okay, let's try object. So we can say like, we can do something like this, right? Like M, I guess we can do this. And perhaps N, I think. Let's try. Okay, anyway. So we have our hash map, and then we pass it in here. We pass it in here. And then we have our type map. Okay, what's it complaining? Oh, again, yeah, of course. It needs the type of the data. Cool. So we have here. So basically, if let's say key, say const key equals M, and then we have M, and then we have N. Do this actually smaller here. So if let's see what I want to see containment. So oops, what's the methods it has? Keys has, okay, has key. So let's replace this. So we know if the key exists, we basically will return that value, right? Because we're gonna store the results of that of the paths. So we say return dot get key. So we have key, yeah, key object. So that's cool. Okay, so we store otherwise. Otherwise, we will store that thing. So we can say like, let's say result, and then we say this, and then of course we say, okay, show a number. Why is this complaining? Oh, okay, yeah, the argument for hash map. Okay, sure. I forgot to add it here. This one, and then we have this one. Now it's not complaining. And then we store that. So we say hash map dot add dot set. So we say key, of course, and then result. Okay. And then we return. You can just return the result. Return the result itself. So let's run this to make sure there's no errors. Yeah, some errors. Call and retry allocation JavaScript heap out of memory. What the hell? Last resort, GCNL space request. Yeah, it seems like I ran out of memory. Let me just try with smaller inputs again. So I'm out of heap memory. Yeah, I ran out of heap memory. Oh my God. Yeah. Okay, I wonder what is it? Why? That's weird. Let's see when it starts complaining. Okay. Compile time error. Oh, I have here. M cannot be used as an X type. Okay, that's weird. Let me, what is this here? Oh, okay, yeah, okay. So what else? Let's just do the same, like 50, and we have like 4, for example. Okay, this is passed. What the hell? Okay, 3 and 7, let's run it. Okay, they did pass. I don't know what was a weird error I got. Okay, let's submit. I mean, they're all passing. Okay, just in case, let's do this one again. 554. Okay, yes. What's up with this? No, they didn't. Yeah, 1, 2, 3. 1, 2, 3. Yeah, 50 and 4. Okay, let's submit it. This should work. Let me just remove this thing. Okay, so let's submit this thing, and it should pass, hopefully. Yeah, still getting this error here. Internal ordered hash table, ordered hash map, allocate. Node.js, mark, compact, reduce, average mu, last resort GC and old space requested. File entry, my God. JavaScript keep out of memory. Let me just see. JavaScript keep out of memory. Um, map. Map running out of memory. This is 7 years ago. Shit. No, not helpful. How to fix a keep out of memory error? Yeah, it's basically. Yeah. Okay. Understanding keep out of memory. Okay, crucial for developers. Blah. Yeah. Okay. This is the heap. Okay. When we create objects, arrays are dynamically. Okay, the heap out of memory when the JavaScript engine such as V8 and Node.js or browsers cannot allocate enough memory space in the heap for an operation. That means that our map is basically exceeding heap memory. Oh, inefficient code algorithms. Great. There are multiple reasons you might encounter. Poorly implemented recursive function or an algorithm with high space complexity that can exhaust the available heap memory. Memory leaks happen when a program allocates memory but doesn't release it. Okay. Large data processing, infinite loops, tools and techniques, browser developers. Oh my God. Okay. Optimize your code. I'm talking actually about optimizing it at the moment. Okay, great. Let me see LeetCode maybe. LeetCode, JavaScript keep out of memory when using map. Yeah, this is what we're doing. Oh yeah, by the way, this technique that we're using right now is called memoization. Yeah, I forgot to mention it. because we're like storing the results. So here we have blah, 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 using memoization to a recursive solution. That's what we're doing. So string blah, okay, where is it? Oh, I don't see, okay, he's not using a, but it's rather slow due to exponential input number. For example, okay, to improve the, okay, yeah, memoize in an update module, blah. Okay, so oh, when I try to run it with the module, just create out of memory, okay. 1.7 gigabytes, which I reckon should be sufficient. Okay. Have you checked how many calls? Oh, I'm actually fetching the resolver function from. I don't know. From changing the resolver function. Where is this? Not really good either. The root issue is that using arrays is what was causing the bottleneck. Behind the scenes, load ash has the. Okay, so it's like doing some load ash thing. Override cache and use weak map. I don't know what the hell this is. Okay, we have some people here. Memo. To wait a bit and refresh the page. What the hell? You know, start using DP. What? Okay. Refresh the page. I don't know if it's like the runtime that's being like used to run this thing. Let me see what error, what test case is this? Let's see 23 and then we have 12. We're gonna delete this guy. And let's run it here before submitting it. Yeah, the same crap. Same crap. Let's refresh it. See. I don't believe it. What was it? 23 and 12? 23 and 12. 23 and 12. My God, okay. Still um um but this should be more related to C++. Um let's call it out of memory when using memorization. Hmm. Oh my God, okay. Why JS needs native memoization? Well, okay, let me see. Oh my God, it doesn't give us any examples. Function memoize. There is a stage one proposal. Check out their proposal page and add use cases and issues and generally help and thank the champions. Well, cache lookup could be slower. Cache lookups, cache uses. Key killing is one sort of this memory management is another. Most memorization in JS mitigate this slow comparison in some way. Lodash, okay. Um, well, let's call it JavaScript memoization, native memoization. Memoizing, what is memoization? Why memoization in React Native? Oh my God, memoization in JavaScript and React. Mm, okay, oh, factorial. Okay, I think we're getting close. Memoization, cool. Here's what memoization function might look like, and here's code pen in case you want to interact with it. Let cache. If you try passing in a recursive function to the memoize function above or memoize from below that, the results won't be as expected since the recursive function on its subsequent calls will end up calling itself instead of the memoize function, thereby making no use of the cache. Just make sure that your recursive function is calling the memoized function. Here's how you can tweak textbook factorial, for example. Equals memoize. Okay. Let's see. Calling the memoize version of itself. The memoize function is caching the values of previous factorials. Yes, kind of memoizing is actually a specific type of caching, or caching can occur. Okay, let's copy paste this example here. So I have it in the editor. Okay. So, okay, so we have this thing here, memoize. I'm gonna make this bigger here. So, so we have a cache, if n in cache. So we have cache n. I want to see what is n. Return args. Okay, let's do the same thing. Let's say const memoize function. Yeah, let's just copy this thing here. And okay, sure. Let's see cache. And then args. Okay, return args. We do the spread operator. And this args. Okay, and this copy here. And so if n in cache. And cache. Okay, let's see. Return cache. Otherwise, we will say result. Not sure. We need to. What should we use memorize in the building thing? Let me just see another more concrete example. So JavaScript memoization Fibonacci. Okay, I think this is the thing we need. Okay, sure. constant fib in memo, return memo. Okay, but this is basically, this is what we have. So maybe, was it a map? Wait a minute. Maybe before I do this, let me try something else. Maybe we don't need, let's just use an object actually. We'll use an object here. And object, not sure if this will also cause the same issue though. So we will have, of course, to update this. So I think no, it doesn't like it. It doesn't like it. Can we add three? I think, could we add them? M plus N perhaps? Maybe. Does not equal, would it be undefined or no? No. So return, if we were in Python, we already finished actually. Return key. Copy paste these for a moment. So we're gonna say hash map m plus n equals results. Not sure if this will work, but let me just reset test cases so it's wrong answer. Output undefined. Let's maybe do this or no, output is undefined. I don't know why. Okay, this didn't really clarify actually. Oh my god. Oh. Oops, did I? Oh my god, I think I stopped recording my screen. Stop recording my screen. Sorry. Okay, if n in memo. Well, let's try that actually. If let's call it here instead k equals n plus m. If k let's see, run. Yeah, this is like not a good thing. I think it seems n plus m. I'm wondering why can't we use key here? Doesn't let us. String, number, or symbol. Ah, well, okay, let's put this into a string. Why not? Okay, so let's make this a string. So we will have, let's just make this like m, and then not sure if we will bring consequences though. creating so many strings here. So key, then we have here key. Let's try here. Key. Okay, key, run. Okay, it accepted it. Now let's try again. What's our 2312? 2312. Yes. Okay, cool. Uh-huh. Okay, so it seems that, for example, that hash map data structure is quite, I don't know, I have to research more about it, but it seems quite weak. I'll have to see the limitations maybe. Maybe we can do a quick Google. So let's submit this thing. Let's submit this thing. Oh yeah, there it is. Okay, cool. Okay, fine. There we finished it. We went into some live troubleshooting. So just for the sake of it, let's get map. Here it is. I want to see if there's like some limitations. Object similar to map, but don't let you set keys. For this reason, and because there were not built-in, the object has been used as map historically. However, there are important differences. Accidental keys. A map does not contain any keys by default. It only contains what is explicitly put into it. Okay. So it can give keys and collide with your own keys if you're not careful. Okay, yes. Okay. Size. The number of items in a map is easily retrieved from its size. Performance performs better in scenarios with frequent additions and removals of key value pairs. And our object is not optimized for frequent additions and removals of key value pairs. Okay. So that is bad. No native support for serialization. Setting object properties. Black browser. Constructor, static methods. Is there like some warnings? Java, script, map, memory limitations. So remember when objects are created on view under. Okay, not 100% sure here. I mean, I'll have to do more, figure this more out, but this is because the video is getting too long. But anyway, this we know that just using a regular object is not really optimized for frequent additions or deletions of keys. But of course, we're always adding. So this might have anyway some performance implication, but it doesn't matter for this particular thing, but just to take into account. Okay, cool. This video really exceeded itself. But yeah, we did some live troubleshooting. And of course, like I mean, I know some JavaScript, obviously. I know JavaScript, but I haven't really done any TypeScript work before. So, but yeah, it's not really TypeScript related, more like JavaScript. In essence, they're almost the same. Okay, so yeah, this is it.